All right, so continuing our journey here into complex numbers. The focus of today is looking at how when numbers are written in polar or Euler's form, operations with them can be done quite readily, even without a GDC. And so let's look at this. I have two complex numbers in Cartesian form. And first, I want to write Z1 and Z2 in polar and Euler's form. So how to do this involves generally, I would always recommend making the Argand diagram first, and then you can visualize more easily what the argument will be and what the modulus or the absolute value would be. That's been discussed several times in previous lessons, so I'll just go straight to it here. Z1 in polar form is root 8 times CIS of pi over 4. Remember, that's a shorthand for the cosine, root 8 times the cosine of pi over 4 plus I times the sine of pi over 4. In Euler form, which I kind of prefer, actually, it's a little bit, I find nicer to write, root 8e times pi over 4 times I. Remember, again, you're not expected to be able to figure those out by looking at them, but we've talked about that in previous lessons. So that's Z1 and Z2. You would get root 2 for the modulus, CIS, and 3 pi over 4 for the argument. All right, Z1, Z2. So the rest of the question is using these to evaluate different combinations of products or quotients. So first, Z1 times Z2. When complex numbers are written in this form, we can evaluate one times another by first realizing I just need to go the modulus times the modulus, so root 8 times root 2. I'm going to go with Euler form, so times E, and then for the argument, it's just one plus the other, so pi over 4 plus 3 pi over 4. Keep in mind that's still multiplied by I. And in this case, notice root 8 times root 2 is root 16, or just 4, times E, and pi over 4 plus 3 pi over 4 is pi, which in polar form looks very similar for CIS pi, which, although I don't have to, just keep in mind is just negative 4. If you were to visualize the Argand diagram of this, you would see that this is on the x-axis, so there's no imaginary component in the end. All right, quite quick. If I divide one by the other, it's quite similar. So first I would divide my two moduli, whatever. So if I were going Z1 divided by Z2, it'd be root 8 divided by root 2 times E, and then I'd subtract. Of course, the order matters, so in this case, it'd be pi over 4 minus 3 pi over 4 times I. And root 8 divided by root 2 is the same as root 4, or just 2 whole, times E, and pi over 4 minus 3 pi over 4 is minus pi over 2, so minus pi over 2 times I. Which, if you visualize that Argand diagram, that argument, you realize this is a purely imaginary number. It's just minus 2I. And so just dividing the other way around, it's just going to be root 2 divided by root 8 times E to subtract these the other way around. In this case, root 2 divided by root 8 is root 1. It's 1 over root 4, which is 1/2. Times E, and 3 pi over 4 minus 1/4 is half a pi, so positive half a pi I. And again, that's an argument of 90 degrees. And so this is a purely imaginary number again, just 1/2 times the imaginary unit. All right, keep in mind these last things I did was optional. That's writing it in Cartesian form, but it's helpful to realize that it's probably a more pleasant form to work with in some ways. All right, so for the backside, let's just look at Z being 1 plus root 3 times I. So first, let's show the Argand diagram and write this in Polar's form and Euler's form. And so even if you weren't asked to make an Argand diagram, I would always recommend it. Both coefficients are positive, so we have a point roughly 1 to the right, root 3 up. I don't know, how about that? There's my vector. And so the argument is going to be this here, which hopefully we recognize this as being a special triangle right there. And so that theta I've shown will be the inverse tan of root 3 divided by 1, which is just root 3. And the inverse tan of the inverse tan of root 3 is exactly 60 degrees. However, we usually use radians for this, so I'll write it as pi over 3. And the modulus, the absolute value, is the distance of that. It's going to be 1 squared plus root 3 squared, the square root of that, which is exactly 2. And so once I know the hypotenuse is 2, the argument or the angle is pi over 3. In polar form, we would get z equaling 2 cis pi over 3, or Euler form 2 times e to the power of pi over 3I. Okay, so next, using just the properties of multiplication, let's determine z to the power of 2 and z to the power of 3. So keep in mind for z, it's probably easier for me to use one of these forms than this if I want to square it. So I'm going to go to Euler form again, just because, I don't know, E is faster to write out than CIS. So in this case, I would just get 2 times e to the pi over 3I times itself. And as we were introduced to in the previous question, if I want to evaluate this, I need to just multiply 2 times 2, which is 4, and then add my arguments together. Pi over 3 plus pi over 3 is 2 pi over 3. Just keep in mind at this point that 2 pi over 3 is too big of an angle for, well, I feel like I've done something wrong here. No, I didn't. Never mind. Scratch my last comment. We're good. We're done. If I want to now cube that, well, I can just take this last value here and multiply it by another value of z. So I'm just going to, for z cubed, I'm just going to take what we had before, because we were already done most of the work, for e to pi over 3 times I, and multiply that by z one more time, by another 2e pi over 3 times I. Same idea. 4 times 2 is 8. 2 pi over 3 plus another pi over 3 is exactly pi. Right. Now that's it. That was fairly quick. However, as we keep going up the powers, it's probably easier just to kind of jump straight to the answer by using this de Moivre's theorem. I apologize if I said that wrong. And so let's show how we use that with z to the power 4. So in general, if I want to take any complex number written in Euler or polar form and I raise it to a power, it can be done quite quickly. For example, if I'd look at z, which is 2e to the pi over 3 times I, if I want to raise it to the power 4, then I just need to raise the modulus to the power 4. I need to multiply my exponent by a 4. And so in this case, I would get 2 to the power 4, which is 16. I get e to the 4 pi over 3 times I. Now this angle of 4 pi over 3 is too big for the convention. Remember, for our argument by convention, we always go no more than pi that way or minus pi that way. So 4 pi over 3 is too much. So we want to visualize what 4 pi over 3 is. Keep in mind, angles in standard position have pop up more and more in this course. So 4 pi over 3 is roughly right here. And so we actually want to look at this angle from there to there, which is minus 2 pi over 3. So we are expected to write in that more familiar, that more conventional form, minus 2 pi over 3 times I. All right, and so for z to the power 5, same idea. This would be 2 to the power 5 times e to the power 5 times pi over 3 times I, which is in this case 32 times e to the 5 pi over 3. Same idea as before, that 5 pi over 3 argument is beyond the sort of constraints of our convention. So instead of going 5 pi over 3 one way, let's go minus pi over 3 the other. And so that's how we want to leave our answer. And that's just recalling from previous lessons the conventions of how we show our argument for these complex numbers. Lastly, z to the power of 6. Why not? Let's do one more. So here we get 2 to the power of 6 times e to the 6 times pi over 3 times I. 2 to the power of 6 is 64 times e, 6 times pi over 3 is 2 pi. However, 2 pi is coterminal with just 0, so we can write this as 64 times e to the power of 0i. Well, 0 times I is 0, and e to the power of 0 is 1, so in the end, this is really just 64. All right, so for this last one, I want to write 1 plus I over 1 minus I all to the power 5 in Euler's form, and I want to do so without using a GDC, and which will allow me to get exact values as well. And so first, I would just write 1 plus I in Euler's form. 1 plus I, using ideas we've heard before, is root 2 times e to the pi over 4I. And just 1 minus I to the power of 5 in Euler's form is root 2 times e to the power of minus pi over 4 times I. All right, now that said, if you look at my denominator, it's 1 minus I to the power of 5. So like we've seen before, if I want to take this to the power of 5, I just need to put that to the power of 5 and go 5 times that. And so in this case, root 2 to the power of 5 is root 32, and 5 times minus pi over 4 is minus 5 pi over 4 times I. Now keep in mind, like I mentioned before, minus 5 pi over 4 is beyond the bounds of how we should write our angle, so that is coterminal to positive 3 pi over 4. And I'll write root 32 as 4 root 2 times e to the 3 pi over 4I. And so now there is my denominator. So if I want to put this together now, I can just take this and write my numerator again is root 2 times e to the pi over 4I, and divide all that by what I just wrote down, 4 root 2 times e to 3 pi over 4I. And using what we've been looking at today, root 2 over 4 root 2 is just 1/4. And then I have pi over 4 minus 3 pi over 4, which is minus pi over 2 times I. And I'm effectively done right here. And so keep in mind, I pretty quickly have an exact value for something that would have been really awful to do if we stuck with it in Cartesian form.